different material, you will remind us.
So I have to apologize to everybody. As it is a continuation of the course, the one who was there 3 weeks ago will see again something we have seen. On the other, I have been much faster this time than the last time, and that's a pity because I will just now present Conley theory, and Conley theory deserves to be very explained in detail because it's a very beautiful and simple proof that I like to present. But let's do a short version of Conley theory. So, when, well, I don't know if it's still the case, but many times for starting a dynamical system, we start by studying hyperbolic dynamical systems, and then you have the notion of structural stability, hyperbolicity, and in particular axiom A plus strong transversality. And there is a theorem that I think many people have seen by Smale. So it's called Smale spectral decomposition theorem. So if you have F, a diffeomorphism from manifold, which is the so-called axiom A plus strong transversality plus no cycle condition. I will not say what it is. That is, if you truly have no idea what it is, I'm sorry. But so Smale in his paper differentiable dynamical system in '68 makes that if you have the condition of hyperbolicity of the non-bordering set, the density of the periodic orbit plus this condition, then if you look at your manifold, you have a decomposition in your manifold in some kind of slides. So it's we call that a filtration. That is, you have here the first M0, which is M1, M2, M0 will be all that. M0 is M, then you have M1, I think it's the contrary. Let's put here Mn, N-1, and here M0 is the empty set. And the thing is that F is going down. That is, if you look at here Mk, you have that F of Mk is included in the interior of Mk. And so you can now look at the part which is in between. And if you look, so Mk minus Mk minus 1. And if you look at the orbit which remains there, so the maximal invariant set, that we can write in formula like that, F, the intersection of all the iterates of this from N in Z, and that will be a compact hyperbolic invariant is because it's a maximal invariant set, compact hyperbolic set, which is also transitive, meaning that you have a dense orbit. Okay, so you get here, and here, and here, and so on, you have hyperbolic set. On all the orbits, if you take any other orbit, what's happened is that it goes down, until it arrives somewhere and stop to this hyperbolic set. So every orbit is coming from one of these pieces. So you have orbit remaining there, orbit coming from here and going from another one. So you decompose the dynamic in blocks which are, in some sense, indecomposable or zable. That is, you cannot decompose because they are transitive. Transitive meaning that you have a dense orbit, so you cannot split in other pieces, smaller pieces. So you break your dynamic in pieces you cannot more break, which are indecomposable, and all the others go from one to another. So that's an important result. But what is interesting is that mostly for having this picture, you don't need no one of these hypotheses is a completely general result in non-conservative dynamical system. And so that is due to Conley on this, what I wanted to speak. Conley. So there is a first paper in 68 and there is another in 88. So on the setting is so general that it is indeed for each from X to X, where X is a compact metric space and H is an homomorphism. So let's present this way. So first we have to replace this notion of being indecomponable, and that is too strong. In general, when you have homomorphism or diffeomorphism even, and you look at the transitive sets, each transitive set belongs to a maximal transitive set. That is not so difficult to check, that if you have an increasing sequence of transitive compact invariant set, the union will be a transitive compact invariant set. But it is not unique. That is, you can have maximal transitive sets which have some intersection. So you will, your dynamic will not split in this set of maximal transitive sets. So you cannot split, this is not a notion that you can make in a too general setting. So you find another weaker notion of indecomposability, which has to do with to be chain recurrent. So I will explain first what is to be chain recurrent, and then we continue. So what we look is pseudo-orbit. So you fix some epsilon positive, and we will say that the sequence xi I in z is epsilon pseudo-orbit. Some author says epsilon chain. If you just have that the distance between f of h of xi with xi plus 1 is less than epsilon. This means that you are considering sequences xi, you consider f, and then you take xi plus 1, which make a small jump on less than epsilon, and you continue like that. You take the image by h, and then you have some other point xi plus 2, and so on. So that is epsilon pseudo-orbit or epsilon chains. If I consider 2 points, x, y, I will make a notation for telling that I can go from x to y by an epsilon pseudo-orbit. I will put like that. I will put x, and I will put some segment, and some things which symbolize a jump. So I will put x, y. And I will put some epsilon there for remembering that it was with some epsilon. Okay, so that means that we can go from x to y by epsilon pseudo-orbit. Okay, that makes a relation. And so I will say that x is epsilon recurrent if for any epsilon you can go from x to x. Okay, that is, you have your x, you choose a very small epsilon, but you can go back. You can make some kind of periodic pseudo-orbit. From x to x with arbitrarily small jumps. Okay. You look at the set of epsilon recurrent points. Not epsilon. That is x is chain recurrent, x is chain recurrent. So I will say f is chain recurrent if it is true for every epsilon. For that I have epsilon disappear because it's for any epsilon. So I look at the set of points which are chain recurrents. And this set is, it's easy to check that it is compact, H invariant, so that is a generalization of all the notion of recurrence that we know. That is, clearly it contains the periodic point of H are contained, but they are contained in the set of recurrent points, which are contained in the omega, the points which are non-wandering. And this set of points which are not wandering is included in this bigger set, in the larger set of points which are chain recurrent. To be non-wandering, I can recall you, means that given x, so omega the h, non-wandering, means that given any neighborhood of x, you have some point here whose orbit go back. How you translate, how you can see that it implies that you are chain recurrent, is because you take the first image, you make a jump here, you follow the orbit of y and go back, making a small jump. So truly this notion of non-wandering is like to be chain recurrent, but only with two jumps, one initial and one at the end. Okay, so we have this inclusion of compact invariant, these ones are not compact, that is two compact invariant sets. So this one has been used for the hyperbolic theory. This one was mostly ignored. But let's see that it is, in fact, a very nice space. So, in particular, because of the... I could almost keep the picture, but I will erase it. But I will have to do again.
Sorry, this might be a stupid question, but you can have a recurrent point which is not chain recurrent? So,
a recurrent point is chain recurrent.
Sorry, that's chain recurrent. Okay, sorry.
Okay. So if you have a recurrent point, then you get in one jump, you allow just a final jump. For the non-wandering, you allow an initial jump and a final jump, and here you allow any number of jumps. That's this difference between these three notions. I think that the first time people see this result is something impressive because with very, so almost nothing, that is homomorphism on this notion of to being chain recurrent. We have this theorem. So, theorem by Conley. So I will take two settings, H from X to X, where X is a compact metric space. Or H from M to M, where M is a manifold, compact manifold. Maybe I should put another color because so that I will can change a little bit the text with using the color. Then there exists a function phi from X to R continuous. With the following properties. First of all, for any point, phi of h of x is no more than phi of x. This means that the dynamic is flowing down for phi, and we call that phi is a Lyapunov function. Okay. Now, if we have equality, that is a point for which is not going strictly down, that is equivalent that X is a chain recurrent. Okay? Furthermore, I forgot something here. So now, before making the theorem, I should show you, explain you why it is good for making a decomposition of the dynamics. And for that, I will introduce an equivalence relation. I will say that 2 points x, y, which are chain recurrent, I will say that they are equivalent, and I will denote that like, that means I can go from x to y, and this will say I can go from y to x, if we have that for any epsilon, you can go from x to y by an epsilon pseudo-orbit, and you can go back from y to x by an epsilon pseudo-orbit. So this is an equivalence relation. On the class of this equivalence relation, are invariant and compact. So this relation split the chain recurrent set in compact invariant set, and in each of them you can go from any point to any other point. That is, you have this incomposability property, but for pseudo-orbit. So now we replace the transitivity for as a notion of indecomposability. We replace it by being able to go from one point to another by epsilon pseudo-orbit for every epsilon, and we get equivalence classes which splits my chain recurrent set in compact invariant subsets. And that is nice because, coming back to the statement, I have this Lyapunov function, and this Lyapunov function makes the difference between any two classes. So if you take 2 points which are chain recurrent, then they have the same image if and only if they are equivalent for this relation. They have the same chain recurrent class. And finally, and I will explain why it is interesting, we have that the image of the chain recurrent set by my Lyapunov function, so it's a subset of R, it has an empty interior. Don't contain any interval, as empty interior. Why it is important, so let me make the picture so that we will see the strength of these statements. So I will just repeat the picture of the spectral decomposition theorem. But here I have this function phi on R. Let's say we can assume it go from 0 to 1 because so 0 here, 1 here. From any point, it goes down. Okay, except if the point is chain recurrent. So you have here, if you have a point here, you have here it's a chain recurrent class. So every orbit, as it goes down by phi, at some moment it has to be stabilized, so it will arrive to some class. So you have the different classes like that. And if you take two different classes, then the last hypothesis says that if you look at the phi of x and here phi of y, 2 points which are, let's say, chain recurrent, then in the middle you have some level where, which is not the image of the chain recurrent set, because this chain recurrent set, its image has an empty interior. So in the middle, you will get some level here with no point for which the orbit is not decreasing. This means that at this place, your dynamic is just going down. So here we recover the filtration of, we get this set which goes strictly inside itself, which was the filtration of the Smith decomposition theorem. So in this setting, we recover the presentation that Smith have done, and that's all for every homomorphism. And furthermore, here I put M compact manifold, and what it changed, almost nothing. It changed that phi is infinite. So you always have a smooth Lyapunov function which separates all the chain recurrent classes. So the classes.
Let me ask you, write phi of recurrence classes as empty interior. Does it mean it is just?
So you can put here
just point.
Totally discontinuous.
But
continuous is the same. If you prefer. It can be infinity, it can be a Cantor set, it can be any compact subset of R with no interior.
you mean empty interiors of what? Of recurrence class or of values of phi?
So,
I don't understand.
okay,
Values
thank
of
you.
phi is just constant.
Thank you for stopping me, because when you want to go fast, you can be too fast. So, you have a class. If you take a class,
Yeah, what is value of
the
phi?
image is 1 point.
Well, that's what I guess. Phi of equivalence class is 1 point. Why?
Yes, that is phi of, if you look at the class,
At the bottom.
phi of the class of X is 1 point. But here I'm not looking.
It is phi of all recurrence.
Now you look at the phi of the whole set of
Okay, not
okay.
not equivalent.
So I
just 1 point.
no, yes. So I say again why it is important, because if you take 2 points and you consider the 2 classes, so you have here the image of the class of X, here the image of class of Y, and in the middle maybe you have infinitely many classes, but you have at least one level where there is no one. So the level is going strictly down. Okay. In fact, that will, I could say that later, but as we start to speak on that, let's finish. For any class admits a basis of neighborhood which is what we will call filtrating neighborhoods. And the filtrating neighborhood is the intersection between that is an attracting region and that is a repelling region. So an attracting region is a region which is a compact region. We go by the dynamic inside its interior. A repelling region is the same, but the negative dynamics. And one of the nice things of this chain recurrent class is if you take a level very close to this one, but without any chain recurring point here. So here you have an attracting region. Now you take below another value with also no one inside. So if you take negatively, it go up, and then so that would be u. You have an attracting region. You take on the other side a repelling region. And if you take the positive iterate of the first one and the negative iterate of the third one, you get something like that. So you get a very small neighborhood, which is the intersection of an attracting region and a repelling region. And these neighborhoods are very useful for understanding how vary my class if I make perturbation of the dynamics. So that I will keep for maybe next time, but it's a useful observation. So now I want to give some word about the proof. So the proof I made last time. So I think it's in. You can see the video, but I will explain very shortly the proof of that. So that's the part. But I'm a little bit sad to be so fast. So let me explain the main idea of the proof. So just what we have is an homomorphism on indeed nothing else. And so we will consider this attracting region and this repelling region. So an attracting region U is some compact, so U compact, so that H of U is included in the interior of U. When you have that, I will denote by AU, and Conley calls that an attractor, so many times attractors will require other property, but here attractors is only the maximal invariant set in an attracting relation. So, as they are compact, that is a sequence of decreasing compact sets, because the image is included in the interior. So that is a non-empty invariant compact set. When you have an attracting region, if you take the complement, you take x minus u bar, that is attracting for h minus 1. Then you can look at what Conley called a repeller, which is the maximal invariant set in this set. Okay. So you have this pair. So mostly you have your x on an attracting region is some region, so you have u here, which is going inside itself. So v, so that is v, that is u. So v by the negativity rate. So here you have h minus 1 of v there. So you take the intersection. What remains here, you call that the repeller associated to R. And what remains when you take all the iterate is what you call the attractor associated to my region U. So I have my two sets. So I have a pair attractor repeller. Okay. What's the relation with what we want to prove? Okay. So I have to erase something. Let's erase what is there. What we prove is that a point is chain recurrent, x is chain recurrent, that is equivalent that for any u attracting region, we have that x belongs either to the attractor or to the repeller. Then we prove that if x, y are two chain recurrent points, then they are equivalent, they are in the same chain recurrent class, if and only if for any u attracting region, if, so we know already that as they are chain recurrent, that both of them have to belong to the union of the attractor and the repeller, and so we require that x is in the attractor, if and only if y also. Something else? No. And finally, so that is one part of the proof. On the other thing is that if you have your attracting, so for any new attracting region, there exists phi u from x to r continuous, or smooth if n is x is a manifold, so that it's a Lyapunov function, but we will have that phi of z is strictly phi of h of z is strictly less than h of z if z do not belong to the attractor nor to the repeller, and phi of the repeller is 1, and phi of the attractor is 0. So for every point, phi of h of z less or equal to phi of z, but I think that is already implied. So what does Conley is, first he re-express the notion of to be chain recurrent in terms of attracting repelling region, and then for attracting repelling region he have some partial Lyapunov function which only separate the attractor from the repeller. Okay? So let's see a little bit why that is true. There is some sense which is clear, that is, I think, if I'm not wrong, there. No, I think it's the contrary. If you have some point, which is, let's check that. You have an attracting region. So you have this u on the successive images h of u, and so on. From there to there is some distance, delta 0, delta 1, and so on. If you have some point which is chain recurrent, it cannot be here. Because if it is here by pseudo-orbit, if you take its image, it goes down by some gap of this delta 0, you make some small jump of epsilon, and you make again a gap down, but if epsilon is much smaller than delta 0, you can never recover, so you are just going down. Okay, so this implies that if you are chain recurrent, you cannot be in these fundamental domains which are just decreasing. And if you are not in this fundamental domain, you need to be either to the repeller or to the attractor. So that tells you directly that if X is chain recurrent, you have to be either there or there. And now if you have 2 points which are chain recurrent, if X is here, Y is there, okay, you can go from X to Y, but you cannot go from Y to X. They cannot be equivalent. So one sense is completely trivial. The surprise, I think, comes from the other side. That is, assume that you have your 2 points which are not equivalent. You have to find an attracting region which contains one and not contains the other. And how you build it, in fact, that is the main surprise of the proof, is that if you take any point x in X, and you consider the set, let's say, you take epsilon positive, and you consider the set of point y, so that you can go from X to Y by an epsilon pseudo-orbit. And this set is an attracting region. Take its closure for being compact. This set is an attracting region. Attracting region. For why is that? Well, this set is a set that you can go from X to the point. By you follow the dynamic, you make a jump of epsilon. And you continue like that. Now take any point like that, so you can go from X to this point by this sequence of jump. Take its image. Now you are allowed to make an epsilon jump around this set. That is, if you look H of that set, and you take now its epsilon neighborhood, let's say epsilon over to neighborhood, this is contained in itself. Which say explicitly that that is an attracting region. So if X is not chain recurrent, it do not belong to this attracting region, but its image belongs to it. So this says that X is not in the corresponding attractor nor in the repeller. And if X and Y are chain recurrent but not in the same class, this means that X belongs to this set but not Y. So X will belong to the attractor and Y to the repeller. So that makes this proof here. Maybe it could be, I have 2 minutes more to speak before the stopping. Okay, so this makes this equivalence here. I know that I'm fast, but I didn't want to spend all my time there. So here, you look at an attracting region, like this one. Then you first, to have a Lyapunov function, if you take anything which is 0 here, y here, 0 there, and between 0 and y in the middle, that's some function which is decreasing along the orbit, but not strictly, because you start by 1, 1, 1, 1, 1, you decrease, and you continue like that. Now you change your fundamental domain, and you take another, you make the sum, and now it decreases twice. But now you can make coefficient, positive coefficients. So you make sum of functions like that, which are y here, 0 there, and in some fundamental domain is strictly between 0 and 1. Now you make sum by coefficients which are whose sum is 1, and which are strictly positive, and you take now a function which is decreasing along the orbit, but remains, which is 1 on the repeller and 0 on the attractor. And for continuing like that, you need to notice, and that it's an exercise, but not so easy, that the pair of attractor-repeller is at most countable, always. So you have AI, RI, the set of all, the set of pair of attractor-repellers. And now you make the same, that is, you have so you get phi I for each of them, and you will have the sum of alpha I, phi I. This one associated to this pair, so that will be a Lyapunov function. We separate the attractor from the repellers, so that gives you all these properties. But now, if you want the last one, you have to be a little bit more careful. So what you want is that if you consider 0, 1 over n, you want, and you associate to omega equal omega I, you associate the sum of the omega I, alpha I, you want that is, the image is a counter set. So if you choose your coefficient alpha I decreasing fast enough so that this map send all the possible coefficient 0, 1 to some counter set, you obtain the last unknown property. Okay. So that is in very, very short proof. That is truly a pity to do that at that speed, because it's something that I like to teach. We need 2 or 3 hours for teaching, for making that. Okay, but yeah, I think first it has been registered. You filmed the first talk, so you can see what and you can find that in any books. So, okay, let's make a break.
10 minutes break.